Now, as we go ahead and we continue talking about waves, and let's go ahead and talk about that energy in waves. Because it says here that a wave is created by a disturbance, that disturbance basically is going to be some energy put into it. If we drop a rock into water, that's technically some kinetic energy if you throw it, could be gravitational potential energy if you just drop it into the water, but an energy is going to be transferred to the medium, and then that medium is going to transfer that energy throughout all of the other particles, therefore carrying that energy from one point to another. Now let's go ahead and let's talk about water waves. Okay, as the wind is blowing, that's going to be that disturbance that we're talking about. But as those waves go crashing against a hillside, as those waves go crashing into kind of a rockiest terrain, say on the ocean, what you're going to find out is erosion is going to occur. So the energy from those waves are going to cause the deterioration and the erosion of some of those rocks. If you have a dirt hillside, you're going to find out that some of that dirt is going to end up being washed away, therefore creating the ground above, making it a little bit weaker. But as we go ahead and we start talking about waves, let's focus on some of the properties associated with waves. I'm going to talk about taking a slinky right now. And if you're holding one end and you grab a partner or tell them and you say, stretch that slinky, go ahead and walk over across the room and put the slinky on the floor. What you're going to notice is that slinky appears in a straight line. That's going to be our rest position. No energy, no disturbances in that slinky, so it appears to be that medium without any energy, without a disturbance in it. But if you start taking your hand and you move your hand up and down or something with the slinky, now we've created that disturbance, and all of a sudden a wave is going to be created in that slinky. The crest, if we're talking about a transverse wave, this is going to be the highest point on that transverse wave. The trough is going to end up being the lowest point on that transverse wave. Amplitude. Okay, so we started talking about energy at the beginning today. Amplitude is going to be a measure of the energy. Okay, a measure from the rest position to the crest of the wave. You know, maybe you've heard people that go out surfing, you know, they talk about 10-foot waves, they talk about 12-foot waves, and things like that. Now, as I've said, this is the energy. You know, maybe you're out at the ocean, and as you're standing in the ocean, the water comes in and it's catching you about shin high. You know, you feel it. But let's say you're posing for a picture, walking along, not really paying attention, and let's say a wave comes in and now catches you about waist high. There's a lot more particles, there's a lot more energy because that wave is going to be bigger and possibly knocking you down. So a wave this big carries so much energy. A wave that is going to be bigger is going to carry a lot more energy. So the height of that wave from the rest position to the crest, this represents the energy of that wave. Wavelength. Wavelength is just going to be the distance between two corresponding parts of a wave. Maybe we say we go from rest position to rest position. Maybe we go from a high point to another high point. Maybe we go from a trough to a trough, but going from an identical point on one wave to the identical same point on the next wave. If you look at the graphic below, okay, they don't call it rest position, they call it an equilibrium position. So if we take that slinky and we stretch it out, okay, there's our slinky in that straight line. But if we put some energy into it, okay, here's the high point, here's your crest, here's your low point, here's your trough. Okay, now we talk about the wavelength. They went ahead and they talked crest to crest. Okay, if we measure that distance there, I'm going to tell you, if I take this point right here, the bottom side of that wave, okay, so if we go ahead, come down here, and I go ahead and I look at this point right here, and I come over here and I measure the same exact spot. So backside of this wave to backside of this wave, if I slid this down here, you're going to find out that that distance is exactly the same. Maybe I go from the trough here to the trough here. Again, it's going to be 100% the same. Now, as we said, amplitude, this is going to be a measure of the energy. So we are going from rest position to the crest. Now, the one thing I do want to tell you is amplitude can also be measured from the rest position down to the trough. Because a wave is perfectly symmetrical, the distance up here and the distance down here is going to be exactly the same. Now, if we go ahead and we continue talking about waves, right now we've just taken a wave and it's kind of been a snapshot, but we know that these waves are going to continuously be moving. And scientists often want to know how many waves pass a point in a given amount of time. And that's going to be frequency. It's the number of waves that we say pass a point in 1 second. Okay? What we're going to do is we could measure 5. We could measure 10 seconds, we could measure 100 seconds, but what we want to do is we want to reduce it down to talk about how many waves in each and every second. Now you're going to find out that frequency is measured in hertz, okay, Hz, and if we say we have 1 hertz, what we're saying is we have 1 wave in 1 second. Now, as I said, we can up the time. Let's say that we have 25 waves in 5 seconds, okay, 25 waves over 5 seconds of time. Well, we can reduce that down to say 5 hertz or 5 waves each and every second that goes by. Now let's look at wavelength and frequency, okay, and let's kind of figure out what the relationship is that exists between wavelength and frequency, okay? And the thing that I'm going to tell you is wavelength and frequency are indirectly related to one another. Okay, so let's say that this is 1 second worth of time, this picture up here, and then let's say that this is 1 second worth of time down here. So if I look at that top picture, okay, notice the wavelength is going to be small. Okay, so let's go ahead and let's bring this down here. That if I say this wavelength here is going to be extremely small compared to this wavelength here, and this wavelength is a lot larger than that distance right there. But if we go ahead and we say that this whole picture here represents 1 second of time, let's go ahead and count. 1, 2, 3, 4, 5, 6 waves pass a point, or we could say maybe even 6.5 waves pass that point in 1 second worth of time. Okay, notice small wavelength, frequency 6.5. Now look here, wavelength is bigger. Okay, so the distance from here to here got bigger, but let's count our waves. 1, 2, maybe 3.5 waves. So when the wavelength went up, notice that frequency went down. Small wavelength, large frequency. Large wavelength, smaller frequency. And that's the reason why we can go ahead and say that wavelength and frequency are indirectly related. As one goes up, the other goes down. Or as one goes down, the other is going to end up going up. So let's look at waves. Knowing that they're moving, we can go ahead and look at the speed of that wave. So to calculate the speed of a wave, wave speed is going to equal wavelength times frequency. Now, what I want to do is I want to go ahead and put in here the symbols, okay? Wave speed, it's just going to be a V, okay? Just like what we had earlier when we looked at chapter 9. Wave speed is going to be represented by the V. Now, you can make up your own letters, but I'm going to be truthful to what they are, okay? Wavelength kind of is like an upside down Y, okay? So that's the Greek symbol. I think it's lambda for wavelength. Now, if for yourself you just want to call it WL for wavelength, I'm okay with that. I'm just being technical. That wavelength symbol is going to be that symbol there. And then what it's going to be is it's going to be multiplied by frequency, okay, F. So V is going to equal the wavelength multiplied by the frequency. If we go ahead and we look at symbols, wavelength is going to be measured in meters. Frequency, as we said from the previous slide, is going to be measured in hertz. And that's going to leave us with wave speed being measured in meters per second. And if you ask yourself, where's the seconds coming from? Remember what we said frequency was. A hertz technically was a wave per second. So what we have is a wave that is a certain distance or meters long divided by seconds, or how often or how many waves go by each and every second. So if we go ahead and we look at that circle equation, okay, and the circle equation is going to look like this. Okay, so setting up that circle equation, there we go. Okay, so there's our wave speed. Wave speed is going to equal, and then we're going to put our wavelength down here and our frequency here. And again, as you remember, we said wave speed was going to be in meters per second. We said wavelength was going to be measured in meters, and then frequency, I'm just going to put up here hertz. As I said, it could be waves per second also, if that's the way you would rather look at it, but meters per second, meters, and hertz. So let's look at an example problem. It says calculate the wave speed that has a wavelength of 0.34 meters if 72 waves pass a point in 2 seconds. So if we go ahead and we look at this, okay, and I'm going to go ahead and draw up here our circle equation. And as I look at that circle equation, it says calculate the wave speed. So I know this is technically what I'm going to be solving for. And on the bottom we had wavelength. Right here, wavelength of 0.34 meters. So I'm going to go ahead and put in here my 0.34 meters. Now, I need to have a hertz. And when I look up here, I don't see a hertz. But if I go back to what my definition of frequency was, it says frequency is the number of waves, okay, number of waves that pass a point in a given amount of time. So there is my waves per second. That's going to help me solve for that frequency here. So if I go ahead and I come back to calculate frequency, like I said, it's waves per unit of time. 72 waves in 2 seconds, that's going to give me 36 hertz. Now I can plug that 36 hertz into that equation that I had right here. I can plug in that 36 hertz down here now. Okay, and that's going to help me solve for that wave speed that we were talking about. So I had to find frequency by taking the wave 72 divided by the 2 seconds. Now we're going to multiply those two. Wave speed equals wavelength times frequency, 0.34 meters multiplied by the 36 hertz that we solved for back here, which gives us 12.24 meters per second. Your assignment is going to be to section 1, talking about mechanical waves and identifying them, and then section 2, talking about those waves in motion.